We're here at the example table, and in this video we continue talking about vertical asymptotes. So the questions that arise now are, what do we do in general to find the vertical asymptotes for a rational function f of x equals p of x over q of x, where p and q are any polynomials? The examples we saw in the previous video had a constant function in the top and a fairly straightforward function in the denominator, so q was fairly straightforward. In those cases, we set q equal to 0 to find the problematic points. Those are where we had vertical asymptotes. So the second question is, do we look only for the values of x for which q of x equals 0? So to answer that question, let's look at an example. Suppose that f of x equals x over x. It's tempting to say that f of x equals x over x is simply the constant function 1. But note that since we're defining it with this formula, we can't plug in x equals 0. So this function isn't defined at 0. Its graph, therefore, looks something like this. It's constant 1 all the way up to 0. There's a hole at 0. And then it continues. So, do we look only for values of x for which q of x equals 0? The answer to that is no. Let's take a look at another example. So let's set f of x equal to x minus 2 over x squared minus 2x. This is a little bit too complicated for what we want to deal with now. So let's simplify, or rather let's factor the denominator. This is still x minus 2, and we can pull an x out of the denominator to get x times x minus 2. Now, for all values other than 2, this is the function 1 over x. So the graph of this is the graph of 1 over x, except at x equals 2. So just like before, we have a hole. In other words, we don't have a vertical asymptote where x equals negative 2, because just as in the previous, x equals 2, because as in the previous example, this x minus 2 factor in the denominator cancels with the factor of x minus 2 in the numerator. So this doesn't lead to a vertical asymptote, but rather a hole. What's left is 1 over x. We still have a vertical asymptote at 0. So this leads us to our general approach. So to find vertical asymptotes of a rational function, p of x over q of x, factor p and q as much as possible, and cancel as much as possible. And let's call the result p0 over q0. So we factor and cancel as much as possible to get p0 of x over q0 of x, possibly different from the original two polynomials. Then p of x over q of x, so let's say y equals p of x over q of x, has a vertical asymptote wherever q0 of x equals 0. Let's take a look at one more example. This time, let's set f of x equal to x minus 2 over x times x minus 2 squared. So this time, we get p0 of x over q0 of x in the notation that we just used is 1 over x times x minus 2. This x minus 2 term in the numerator cancels one of the two x minus 2 terms in the denominator, but we're still left with another one. By this general approach, we now know that f has vertical asymptotes when x equals 0 and when x equals 2. So let's finish by figuring out what this graph must look like. So we have a vertical asymptote here. I won't put a dashed line. We also have a vertical asymptote here at x equals 2. Now, it's worth noting that this function has no intercepts with the axis whatsoever. We can't plug in x equals 0, so it doesn't have a y-intercept. And neither of these expressions is ever equal to 0. That's easiest to see here because 1 over something can never be equal to 0, so it never intersects the x-axis either. So that's going to help us in a moment. Let's look at what happens on these three intervals. We have two key quantities. We have x and x minus 2. For all values of x greater than 2, x is greater than 0, and x minus 2 is greater than 0. For values of x between 0 and 2, x is greater than 0, but x minus 2 is now less than 0. And for all values of x less than 0, well, x is certainly less than 0, and x minus 2 is less than 0. Why is any of this relevant? Well, this tells us what the sign of this thing is going to be. So for these values of x greater than 2, this function is going to be positive. For values of x between 0 and 2, these two quantities have opposite signs, so the function is going to be negative in between here. And over here, these two terms have the same sign again, so it's going to be positive. So I'll leave it to you to convince yourselves that on this side it looks like this, roughly, and on this side it looks like this, again, roughly. The question is, how does it behave in between here? Now, I'm going to use the idea of continuity. This function isn't going to have any breaks or any kind of thing like that except at these asymptotes. That's something that we can talk in greater detail in a calculus course. What do we know? The function never intersects the x-axis, so it's going to be either completely above or completely below. This is always negative, so we now know that it's always below. As we approach either 0 or 2, we know we're going to approach negative infinity. So we are more or less forced, because this is a fairly well-behaved function, for the graph to look something like this.